what if it's not a constant field? What if it's not a flat surface? So what if I have a field that goes every which way? What if I have a field that goes every which way and a surface that's curved? Well, in general, what I'd have to do is I'd have to go to some little spot and I have to say, okay, well, what's the area of this little bit? What's the perpendicular component of the electric field there? And like get a little bit of flux from that, you know, take the dot product of those, and then I'd have to come to the next little bit and 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 kind of tile over my whole surface and figure out at each little point, what's that dot product? And in general, this is going to give me something called a surface integral. Now, for most of you, you have probably never done a surface integral before. And I'm here for you with some excellent news. You won't have to do them really in this class. We'll kind of be doing them, but not for real. So in general, this would be some kind of surface integral. For those of you in multivariable, you do have to do some surface integrals. So let's take a look at some special cases. Well, here's a case where we have our electric field everywhere being perfectly tangent to our surface, perfectly parallel to our surface. Well, in this case, how much of that arrow is actually going through our surface? And the answer is, well, none of it. It's always perfectly perpendicular, or excuse me, perfectly tangent to our surface. So none of those arrows actually go through. And as a result, the flux there is zero. So the net result of our whole complicated surface integral, whatever it would be, would just give us a big fat zero. What about in this case where our electric field is everywhere perpendicular to the surface? Well, if it's everywhere perpendicular to the surface, each little contribution, EA cosine theta, is just going to be E times A. If it's everywhere perfectly perpendicular to the surface, then everything is constant, and we just end up with our flux being E times A. And what I'm here to tell you is some very good news. Every flux integral you do in this class will be one of these two kinds. Either the flux will be everywhere tangent to the surface, in which case there's zero flux, or it'll be everywhere perfectly normal, perfectly perpendicular to the surface, in which case it's just multiplication. It's just E times A. So that's very important. You will not actually have to do a surface integral here. You just have to look and figure out, is it tangent? Is it normal? And then do the right thing there. So let's take an example of this. Let's look at this cylinder. What is the total flux through here? So I want you to take a moment and try to work out the total flux through here. Well, if you said zero, you were right on track. But let's break it down a little bit more and look at our different faces. So let's look at this red face first. This has an area of pi r squared. And let's see, the electric field here is always perfectly perpendicular to the surface. So this is one of those ones where it's just E times A. So my flux through here is going to be E times pi r squared. And in this case, is it going to be positive or negative? It is going to be negative because the flux is going in. Let's come to our other little end cap at the other end. Same deal. The area is still pi r squared, so our flux here is going to be positive E pi r squared. So far, so good. Let's think about the wrapper, though, of this cylinder. It has an area equal to 2 pi r, and I suppose I need to write how long the thing is. It has a length L, 2 pi RL. But what we notice is that those electric field lines are everywhere perfectly parallel to the surface. So if they're perfectly parallel to the surface, the flux through that part is zero. So even though we have a curved surface, we can still use that same intuition and argue that it's perfectly parallel, and so that the flux is zero. So we have negative E pi r squared coming in, positive E pi r squared coming out, and zero on the wrapper. So our net flux is still zero. And again, a really good way to think about that is, look, every single electric field line that enters leaves. So our net flux is zero. Okay, Why the heck do we care? The reason that we care is because of this guy, Carl Friedrich Gauss, looking kind of like a hobo there. And Carl Friedrich Gauss came up with this beautiful law called Gauss's law that says for any closed surface enclosing some amount of total charge Qn, the electric flux through that surface, the net electric flux through that surface, remember here's our flux, is exactly equal to the enclosed charge divided by epsilon naught, divided by that constant epsilon 0. The total flux, no matter how complicated it is always equal to the amount of charge enclosed divided by epsilon naught. And what this basically says is exactly what we've been saying. I can tell what kind of charge is in a box by looking at the flux of electric field coming out of it. And conversely, if I know what kind of charge is in the box, I can make a lot of really important inferences about the electric flux coming out of some surface. And it turns out that we can make these integrals very easy and get some really, really, really powerful results by choosing the right closed surface. So it says for any closed surface, this is true, but some surfaces are better than others. So we're going to talk now about how to choose the right Gaussian surface and what the heck it is. So we know how to calculate flux. Excuse me. We know how to calculate flux. Now we need to figure out what the heck this closed surface stuff is all about. A Gaussian surface is, like it says, a closed surface through which an electric field passes. And it's very important to note that this is an imaginary surface. You are sketching in this Gaussian surface. It doesn't exist already. So as an example, if I have some big wire full of charge, one of the decisions we're going to have to make soon is how to sketch a Gaussian surface. And again, Gaussian surfaces aren't real, but we can still sketch them in. We can kind of pretend, okay, I'm going to draw this closed cylindrical surface around my wire. So they are imaginary surfaces that we're going to draw in to meet our particular needs. So they're not real, but we do still need to draw them. We do still care about them. And our goal with a Gaussian surface is to make sure a couple things. One, we have to make sure it is closed. Gauss's law doesn't work if our surface is not closed, because again, a non-closed surface doesn't really provide enough information about the charge. If I don't have a closed surface, I don't know whether it's negative charges over here or positive charges on the other side. I don't have enough information. I do want it to match the symmetry of my charge distribution. So here's an example where it doesn't match the symmetry, and we'll find that this isn't very useful. It makes if it doesn't match the symmetry, it's going to make our evaluation of the flux very complicated. And ideally, we want to make it so that the electric field is either tangent to our surface or normal to our surface. And we're going to draw 3 different kinds of Gaussian surfaces: boxes, cylinders, or spheres. So pretty much every Gaussian surface should be one of those 3, and your job is to pick the right one. So let's take a look at this. What kind of symmetry does this field have? Was it that planar, cylindrical, or spherical? And therefore, what kind of Gaussian surface would be best? Well, if you answered that it has cylindrical symmetry, you were correct. And as a result, you might guess that we want to draw a cylinder, but we don't want to just draw any old cylinder. We want to make sure that our cylinder is symmetric about our charge distribution. So here, I would probably draw it so that the wire is in the middle, with our cylinder kind of enveloping it all around. So you want to make sure that it is nice and symmetric. It is centered. It is centered there. What about this one? What if I have a single point charge? So single point charge, what kind of Gaussian surface would I use there? What kind of symmetry does it have? If you said spherical, you were right. So obviously this is 2D, so I'm going to kind of cheat a little bit, and I'm going to draw a circle, but we're going to remember that it's a sphere. And let's actually use Gauss's law to find this electric field. All right. Well, if I draw that sphere, Notice, by the way, that my electric field is everywhere perpendicular to the surface of my sphere, which is nice because that means that my flux integral, if it's everywhere perpendicular, remember, it just ends up being the strength of the electric field times area. Well, what's the area of my sphere? It's kind of interesting. I don't know. I can draw a sphere, this Gaussian surface, as big as I want, as small as I want. So let's just be specific. And whenever I draw a Gaussian surface, let's give it some dimension. So I'm going to say that it's a sphere. It has a radius r. So this is my electric field times, well, I know the surface area of a sphere is 4 pi r squared. All right. So far, so good. Now, what Gauss's law assures me is that that flux is exactly equal to the enclosed charge over epsilon naught. So let's try that. So here's my flux, E times 4 pi r squared. How much charge is inside my surface? Well, Q, it's right there, over epsilon naught. And what's kind of interesting is I can now solve for E. I can solve for the strength of my electric field. And solve for the strength of my electric field. It's also worth noting that not only is it perfectly perpendicular, but because my field is spherically symmetric, I can be sure that the strength of the electric field over here and over here is exactly the same because my distance is the same. So let's do a little solving. Okay, I'm going to divide, and I'm going to end up with E equals 1 over, I'm going to write this in a very particular way, 4 pi epsilon naught Q over r squared. Oh my goodness! That is exactly what we found. That's exactly what we knew already from Coulomb's law. Gauss's law allows us to actually prove what the field for a single point charge is using nothing other than our understanding of flux. So for a single point charge, Gauss's law tells us that the total flux is related in this way so that our electric field ends up being exactly what we thought it was, KQ over r squared. It's important to note that different kinds of surface, this makes it very easy even for weird surfaces. So how much flux, what is our net flux through that surface? And there's a little hidden question here, how much charge is enclosed? And again, there's no charge in there. So because Gauss's law tells us that the total flux has to be equal to Q enclosed over epsilon naught, if there's no charge in here, the net flux has to be 0, no matter how complicated the field. So Gauss's law tells us some very, very, very useful things right away. Last but not least, I would like to leave this to you as a little bit of a challenge. I would like you to show me, if possible, that what the electric field of an infinite plane of charge is. We're going to assume that it has a density on the surface of this little nu, and I'm just going to help you out, that the amount of charge enclosed right here on the plane is going to be, if you've got a little end cap here of size A, it's just going to be n times A. So they've actually already drawn in the Gaussian surface for you. But your challenge is to try and demonstrate to me, or for yourself, that the strength of the electric field in this case, using Gauss's law, is going to be given to us in quite a straightforward fashion. And it is going to be, let me think about this for a second. So it should just be this over it should just be that, and that it doesn't depend on distance. So we will do that one in class. Thank you very much, and have a great week.